Welcome to this lecture series in group theory. In today's short lecture, we will discuss the notion of direct products, and all we need to know are basic definitions, what is a group, and what is meant by the order of an element. Let me not get into the details of these things because we have discussed them many times. All right. Some problems for practice. And now let us get started. So whenever we are given two groups, G and H, could be finite, infinite, anything, we can define something called the direct product of G and H as follows. So as a set, G cross H, I mean the notation for direct product is G cross H. And as a set, it is just the Cartesian product of G and H. Maybe I'll write little g, little h. So it's just the Cartesian product, but what is the binary operation? You can guess. Let me not write it very formally, but the binary operation is the following. If you multiply G1, H1 with G2, H2, the output is G1, G2, H1, H2. So what's going on is there is a binary operation on G and there is a binary operation on H. We are just exploiting both of them to give a binary operation on this guy. This dot is what we are defining, and here the binary operation is suppressed, and same here. There is a binary operation on G, so this makes sense, and similarly this makes sense, right? So it's the most natural definition of a binary operation that you can come up with on this guy. And the fact is that this is a group. So this makes G cross H under this dot, which again we suppress, we do not write it. This is a group. I've written it here, but in general we do not write any notation for the binary operation on the Cartesian product. Unless it is very much needed, sometimes it might be needed. Sometimes we might need to explicitly write down a notation for the binary operation on G and one for H because some confusion can be caused. Okay, this is a group. Why? First thing is associativity. Well, that is a simple exercise. It is a simple consequence of the associativity of the binary operations on G and H. Right, so it is associative. I'll just write associative. That's easy to check. For identity, this pair EG, EH. So by EG, I mean the multiplicative identity or the identity of the group G, and EH is the identity of the group H. And this is the identity of G cross H. And lastly, for inverse, G inverse, H inverse is the inverse of G, H. Right? Everything is extremely simple. You can immediately see that this is the case. Okay, so we have a group on this group structure on this set. So whenever we are given two groups, we can create a new group out of it, and you can extend this definition to take direct product of arbitrary collection of groups. So for instance, if we are given, let's say, finitely many groups, G1 up to Gn, then we can consider this guy, which we can define just like this. So I'll leave that to you. In fact, you can take a Cartesian product of uncountable families also, that you can do, but we will do that or get into the details of that if needed. Right now, we are happy with just finite Cartesian products. Okay, an example, we have previously seen this group Z2. It was visualized as this grid. You know, the dots here, they are the elements of Z2. But if you think about it, it is exactly the Cartesian product of Z with itself. The group Z with its usual addition, I mean the set Z with its usual addition is a group. And if you take the Cartesian product or the direct product, I shouldn't say Cartesian product, I mean the direct product of Z with itself, you get Z2. And similarly, you can see that Zn is just the n-fold direct product of Z with itself. So I'll leave you to verify this. It's hardly anything to do there. Anyway, next example, little more interesting. We can take Cartesian product of z with z mod n z. This with its usual addition and this with the addition that we discussed. And this you can think of as a discrete cylinder. So z is like the discrete version of a line, and z mod nz is like the discrete version of a circle. Right? So you can think of z cross z mod nz as a discrete cylinder. Maybe I'll put the circle here because it's an infinite cylinder going infinitely in both directions. Not the best diagram, but I hope you understand what I'm trying to say. Just take the discrete version of it. So there are some dots here, and for every dot, there is a copy of z mod nz. For every dot, there is a copy of z mod nz. That's how you can visualize it. Okay? And you can also take direct product of z mod mz with z mod nz, and this you can think of as discrete torus. If you cross product two circles, suppose you cross product s1 with s1, that you can visualize like this. There is this copy of the circle s1, and for every point on s1 there is a copy of another s1, which we can think of it like this. Right, so s1 cross s1 is a torus. This is the discrete torus. So s1 cross s1 is also a very nice example of a direct product. I should have made separate point for it, but I am a bit lazy now. Okay, so there are infinitely many examples that you can construct. Some of them you can visualize. Let's just note a few points. Suppose G and H are abelian, then this guy is abelian. That's a very simple exercise. And if this guy is abelian, then these two are also abelian. That is also a very simple exercise, but let's maybe write something towards that. So assume this is abelian, and if x and y, or let me say g1 and g2 are in G, then g1 comma EH times g2 comma EH, this by abelianness of the direct product is same as g2 comma EH times g1 comma EH, which gives g1 g2 comma EH is equal to g2 g1 comma EH, which if you just compare the first coordinate or the first entry, you get g1 g2 is g2 g1. So that shows abelianness of G. Similarly, you can prove abelianness of H. So there is not much to it. Also, yeah, this is interesting. Suppose X is an element of G and Y is an element of H, then the order of this guy, order of X comma Y, is the LCM, the least common multiple of the order of X and the order of Y. So when we write order of X, of course, we mean the order of X in G. X is an element of G. And when we write order of Y, we mean order of Y in H. So we can take LCM of these two numbers and we get this. So one thing I should say, suppose order of X is infinite, then this will be defined as infinite. Okay. So why is this? In case order of X is infinite, I mean the infinite cases I leave as an exercise. Even this should be left as an exercise, but here is the thing. Suppose they are both finite. Suppose order of X is, let's call that M, and order of Y is N. And let's say order of X comma Y is D or something. I don't know what I should say. Let's say it is equal to, let's run with D, although I don't like D here. So we know that X comma Y to the power D is equal to X to the power D comma Y to the power D. That you can easily check, right? But since D is the order of X comma Y, this thing is equal to E comma E. This is the identity of the group G cross H. So this is equal to E comma E, or I should say EG comma EH. And you get x to the d is e, and y to the d is eh, and hence d is divisible by the order of x and d is divisible by the order of y. So d is a common multiple of order of x and order of y, and hence it is at least the least common multiple of order of x and order of y. So this shows that d is at least the least common multiple, but you can also easily check that in place of d, if you write the LCM in this equation, in place of d you can write the LCM of order of x and order of y. That will make this equation true. So you can fill up the rest of the details. I have done sort of one direction, the other direction you can do. So this is all that I wanted to say. I didn't want to say much. This was just a very short, supposed to be a very short lecture. We will revisit direct product later when we will discuss homomorphisms, and this concept will recur over and over. This is the analog of the direct sum in the world of vector spaces. Alright, so it's a very, very natural and useful construction. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.